Okay, so in this video, as you can see, I'm going to be talking a lot about acceleration. So, like I said before, acceleration is going to play a big role into this class just because it all revolves around the sum of the forces equals mass times acceleration. So yeah, it's you're going to have to deal with it a lot. So you better get used to it. So anyways, so basically, there's two forms of acceleration. So normally, we're just normal to using with the Cartesian form where we have ay and ax. But I want to talk more about tangential acceleration and centripetal acceleration, or in other words, normal acceleration. So the reason why it's called normal is because it's the vector points normal to the velocity vector. So it's just perpendicular. It points inward. So anyways. So we're not dealing with Cartesian vectors, or Cartesian coordinate necessarily right now. So just to start off, I'm gonna show how we get this. So a lot of it deals with the cross product and dot product and whatnot, but I'll show you the simplest proof for it, I guess. So you have your arc length formula in the end. So it's really just S equals R times by theta. So in the end, here, oh, yeah, okay, yeah, I want that guy. So let me just make a good circle. So a little bit more, okay. So we have this circle, and let's get rid of it. This was the center. So if this is R, your radius is R, and measuring theta in the end, this length right here is going to be S. So that's your arc length. And you can see this happen like with just a full circle. So if you go 2 pi radians or a whole revolution, you're going to get 2 pi r. And 2 pi r is literally the circumference, So C equals 2 pi r in the end, So, or pi times by your diameter. So same thing. So anyway, so that's really where the arc length formula comes from. So I'm going to erase some of this. So we'll just leave the circle up for right now. So really, when you take the derivative of this with respect to time, and you assume that the radius isn't changing, then you get then you're going to get basically ds dt equals r d theta dt. So in other words, you have your velocity equals your radius times by your angular velocity, omega. So you're going to use this a lot too. So velocity, you don't have a tangential and normal velocity, you just have a tangential velocity. Velocity is always in the tangential direction. So it's not, you can't break this up into components where it's tangential and like centripetal. So, so anyways, so now if we take the derivative of this again, we are going to get acceleration equals r times alpha. So, so as you take the derivative of this, dv dt is acceleration, d omega dt is going to be alpha in the end. So I could write that again like this, but that it's the same thing. So okay, so now that I have everything erased, basically we're going to talk about centripetal acceleration. So here, let me first write down. So we said that velocity is equal to radius times by omega in the end. So velocity is more or less speed. Velocity is basically it's the vector form of speed. Speed is just the magnitude. So typically, when you're going to be doing all this, you're going to be working with speed or with velocity. So, but it won't just say speed. It'll just say velocity. So, it's almost tomato, but it's almost if you like put another vegetable in there too. So anyway, so it's different, but it's not. So anyways, so we found out this last time also, and So basically, in the end, centripetal acceleration in its more formal version is just velocity times by omega. So as you can see, if you solve for velocity right here, you get v over r. That's equal to omega. If you plug in omega and what omega is right here into here, you get v squared over r, like you saw. So and now if you just want to work with omega, then just plug this in for v, and then you get r times by omega squared. So yeah, so in the end, you're going to have these two forms of acceleration. So now that I have basically shown what they are in the end, like the equations and everything, I'm going to show how they behave now. So because that's very important. A lot of people don't go into that at all. So we need our circle again. So now here. So yeah, so just imagine we're going clockwise, you know. So in the end, if we're going clockwise, if we're at this point, we're going to be going up, technically. Our velocity is going to be up. So so really, if you have just centripetal acceleration, so I'm going to write that down. So just AC, so centripetal acceleration. You're going to have, basically, your speed is going to be constant in the end. So it's going to be constant, but really, acceleration is the change in velocity. So technically, your magnitude is going to be the same, but it's just your direction is changing. So you know, so really, this is like change in direction in the end. So and that's pretty much all that it is. So really, you're just changing the direction of your vector. And technically, since that's still a change, you know, you have to account for it as acceleration. So, so really, here. So, actually, let me redraw that. So, it all should be around the same size of a vector in the end. So, and then you have this. So yeah, so as you see, it goes in a circle, and its speed is constant. So now that's centripetal acceleration. Now we're going to be talking about tangential acceleration. So since centripetal acceleration is the change in direction of these vectors, well, what do you think tangential acceleration is? Well, it's going to be the change in magnitude then, you know, just because vectors are made up of direction and magnitude. So it's going to be the change in magnitude. So what's really going to happen to these vectors is that they're going to increase, you know. So really, it's going to get longer is all. So this is more tangential acceleration, while this is centripetal acceleration. So really, you're changing the speed of just changing the speed. So it's the change in speed. So yeah, so that's pretty much it, you know. So I like to draw this diagram because it shows it real well, you know. If you go in a circle, technically your velocity is changing, you know, even though you might think, oh, well, it's a set number. Well, you're not dealing with numbers anymore. You're dealing with vectors. So and if a vector is changing, it's either changing in direction or it's changing in magnitude, you know. So I'm also going to write magnitude right here, you know, magnitude. So change in direction or change in magnitude. And that's pretty much the difference between tangential acceleration and centripetal acceleration.